point? Like, where do I point? On the... No, no, I'm giving away my talk. How does it work? Can you see the pointer? Yes, okay, so I should point there. Okay.
All right, so the second and last session of the day, we have Michele Del Zotto, who will talk about gap phases of 40 QFTs with non-invertible symmetries. Take it away.
Hello. Thank you very much for inviting me. It is a pleasure to be back in Trieste, my alma mater, and to have an opportunity to meet with this community that is working on CFTs, quivers, and also symmetries, and to have a chance to discuss with all of you. And I'm really happy to see many faces that I wasn't seeing for a while. So thank you to the organizer for putting this together. It's very nice. And let's hope this is just the first of a series of meetings. So I want to discuss some results. I was a bit uncertain about the topic of my talk, and I ended up converging on this one because I think, like in the context of non-invertible symmetries, there are several techniques that have been developed to speak about generalized symmetries, in this case non-invertible ones, that will have a lot of generalization and possible application also in the context that we care about, like quivers and superconformal field theories that have been explored partially, but not at full glory. And so I wanted to review a little bit of these aspects and discuss the case of 4D QFTs where this can be really analyzed and beaten to death. And the case of 4D QFTs have been studied more because it's the case where we have confinement and there are applications in that context that might be that were like more stringent, more pressing for the community. So this is this seminar is based on joint works with some collaborators. My former student Elias Riedel Gårding graduated in September. Azeem Hasan was a postdoc in Uppsala when this project started. Cantaro for many discussions, and then also Federico and Ruben for some aspects. The papers with Cantaro, Ruben, and Federico are in preparation. The one with Elias and Azeem is out. It took a while. It's a paper that we published in April. And then there is also some work in progress. So there are no references in this talk. I apologize to the many experts in the audience for this, but I want to point out some papers that were really crucial for our study and inspired it. So these are the papers by Kaidi, Omori, and Zheng on the SymTFT for non-invertible symmetry of 2022. This paper, a triple of papers, one by Antinucci, Benini, Coppetti, Galati, and Rizzi, one by Cordova, Xin, and Zheng, and one by Sung and Zheng. All of 2023 that came out more or less at the same time, where anomalies for non-invertible symmetries in 4 dimensions were discussed. And also a paper that of the same year by Aguilera, Damià, Argurio, Benini, Benvenuti, and Coppetti about the interplay of non-invertible symmetries and RG flows. And when this paper came out, I found them extremely interesting, and I tasked my student and my postdoc to let's do a systematic analysis. Let's try to work solve this problem in 4 dimensions. And like we haven't done it completely. We did a first coarse classification of gapped phases compatible with non-invertible symmetries. There is a lot of work to be done in this direction, and I'd be happy to discuss it afterwards if you are interested. And for references, of course, I direct you to the papers, and also the one that is published as a thorough bibliography. Feel free to ask me later if you're also interested. So that's okay. So the key, yes.
So 3 dimensions, is that classification?
Not that I know of. Maybe there is, maybe I don't know. But yes, the logic is going to be essentially the same. I will discuss a logic that is universal in all dimensions, but the details of it are like are dimension dependent because the SymTFT that we use will depend on the dimensionality of the theory under consideration. So the context is essentially the interplay of symmetries and RG flows, and the question that we want to ask is the usual question in quantum field theory: what is the interplay between macroscopic and macroscopics? No. So normalization is, of course, we know, very hard, and symmetries are a tool that we can use to constrain the properties of the RG flow. And in today's talk, I want to review some implication of generalized non-invertible symmetry to constrain gapped phases in 4 dimensions, so phases with a mass gap. Now, generalized symmetries, I don't know, like many people in this audience probably don't need a review about this, but the philosophy is essentially that, okay, we want some symmetries that can give rise to conserved quantum numbers for extended operators, and they were constructed by Kapustin, Seiberg, Wichtel, and Gaiotto back in 2013. Case of P-form symmetries associated to conserved P-form currents. You can obtain some operators. There are examples, for instance, in the Maxwell field that's where the higher symmetry follow from the equation of motion and the Bianchi identity. And like this is a well-developed subject, and these are all examples of topological operators of a given codimension, so the P-form symmetry of codimension dp minus 1. And once one introduces these extended operators in the quantum field theory, one is faced with additional quantum numbers. There are quantum numbers that come from the crossing of a topological defect. You can take a line, cross a topological defect of a given codimension, and have an action of one symmetry on the other. Or an action of a symmetry that would act on certain operators on other operators of different dimensionalities. And also they have a Higher structure. So you can think of these Higher symmetries as some sort of topological membranes. And these membranes can intersect, can fuse, can merge. And whenever they intersect and fuse and merge, they give rise to other topological membranes of lower dimensions. And also those can act on the spectrum of the operator. So it's very interesting to study the Higher structure of symmetries and to study its interplay. So for instance, anomalies that we know and love, they are part of the data that you can find within the Higher structure of the symmetry. And there are further properties, further quantities which are encoded in the Higher structure that has the same feature of Tooth anomalies. So if you match a non-invertible symmetry across an RG flow, the whole Higher structure has to match, and this gives rise to a lot of further integers that you can match along the RG flow, giving rise to generalization of Tooth anomaly matchings. No? So it's interesting to study this, and it's further data on the problem, and one is led to the claim that topological operators and defects define generalized symmetries. No? Of course, these are not symmetries in the standard sense; they are generalized, and like the proper one possibility is to state that this is actually the definition. So all the examples of generalized symmetry we know following this category, but there are more. So now, then the task is how do we characterize these defects, and how do we characterize a subset of the QFT of interest that consists of topological operators? No? And so far, the community has developed two possible approaches. One is the word volume approach, and another is to realize the theory as a bulk boundary system. So the word volume approach is very direct. You have your quantum field theory, you have your Lagrangian, you have some action, and then you study the possible topological defect that you can construct with those fields. No? You look at them, and oftentimes it can happen that along the word volume of these topological membranes, there are topological degrees of freedom that are supported and that are crucial for guaranteeing the topologicalness of this discontinuity in the quantum field. And that's very, very direct. And it's possible to compute the Higher structure directly from the word volume. And then there is another way, which is realizing your theory as a bulk boundary system, which is called the topological symmetry theory. And that's the approach that we will take for today. And you have heard about it a little bit during the talk of Sagar, but I will review it because repetita iuvat. So how does it work? Let's consider the case of finite generalized symmetries, because that's the case that we will focus on mostly in the talk. And we all know that if symmetries are anomalous, you can have an anomaly in flow. No? So what is anomaly in flow? The idea is that you have your theory, and you couple it to background fields, and then you perform some background gauge transformations, and the background gauge invariance is broken. No? But there is a way to fix it if you add an additional dimension to your field theory. No? And so this is the picture of anomaly in flow, which we learned in string theory when we studied M5 branes, essentially. So it's nice, no? And you just add a phase, no, to your theory. The field A here, which is the background for the symmetry, is just a background field. You're not integrating on it. So you just add a phase in one extra dimension. And this phase, oftentimes, since it is a phase, is called an invertible field theory. No? And it satisfies axioms of topological quantum field theory. It's interesting. It's an interesting quantity to study. So we know that this thing exists. So how can we use it to build a SymTFT? We just promote this bulk, this invertible theory to finite gauge fields. No? And when we do that, we still obtain a topological field theory. It's just that now it's a more interesting one. No, it's not just a phase. It is a theory that has some topological structure. It's non-trivial. Maybe it has some finite gauge fields that propagate. and it will have some topological operators that are more interesting than the one we started from, but it's still topological. And so there is a possibility of establishing an isomorphism, no? With this isomorphism that relates this bulk to the boundary. No? So this is the data that we have. So we have our theory that we wanted to begin with. No, we have its anomaly. We do this gauging. We end up with a system, which is a bulk boundary system that has a topological field theory here, a topological interface between this topological theory and the original inflow action, and then another theory here. And this, oh my God, this theory here is not exactly the theory we started from. Like, because here we have gauged the bulk. It's some relative field theory, and the contraction that arises because the bulk is topological, so it doesn't really care about the size of the interval. So it's literally an isomorphism between the system on the left and the system on the right. No, and whenever we have an isomorphism, we can build a dictionary. No, and this dictionary is the key that one uses to unpack the topological operators. No. So of course, once you have established this, you can switch off the background fields. No? And if you switch off the background field, you end up with just the bulk and the boundary, no backgrounds now. And you can, if you're interested in characterizing the topological defects of your field theory, you can just work with this setup. You don't need to have background field switched on. So this is the context that we will use, and in this context, it is nice to think about how do we realize the topological defects. They arise from topological defects in the bulk. No, so if they end on one side and the other, they give rise to charged operators. If they don't, they are supported on this boundary essentially. They give rise to the topological defect that we can use to compute the quantum numbers. No. So the endings, especially on this side, does not need to be topological. No, this is the ending is the location of the extended defect that is charged with respect to the generalized symmetry. And from the properties of the linking of this defect in the bulk and their interplay with the topological operators in the bulk, you can read off the action. And this is essentially a generalization of a representation of a group, if you think about it. So this is essentially the datum of the group, and this is the datum of its representation, how this ends. No? And it's important, one thing that needs to be stressed in this context is that this allows to separate the problem of characterizing the structure of the topological operators from the dynamics of the field theory, because the dynamics happen all on one side, and the structure of the symmetry happens all on the other. No? So things we have heard several times. A remark that is in order here is that this setup is very reminiscent of holography. No? So also in holography we have an isomorphism. No? And there is a bulk theory, which is gravitational, and there is a boundary theory. No, this is a collection of boundary conditions. However, the holography that we have heard about earlier in this context is a much richer isomorphism. No, from holography we can capture everything of the quantum field theory. Instead, in the symTFT, we just care about the topological defect. It's some trivial version, if you like, of holography. No. However, one can try to ask, well, can we obtain the symTFT from holography? Can we use this more powerful bulk boundary system dictionary to compute the symTFT? And that can be done and has been done by various people in the community. And one can recover results about the global structure, one can recover the world volume theories of the defects, and also has understand, maybe guide generalization to the case of continuous symmetries from holography, because in holography we know how to describe it, and one can try to essentially extract the topological sector of the ADS background, and there are various ways of doing that, and various caveats in that context. So this is something that, like, for the people in this audience, can be interesting to explore or explore further. Same thing we heard about it in Sagar talk. There is a realization of this in geometric engineering. So if you have a CFTs that arise from a conical singularity in some string theory background, there is a way of finding the symTFT from geometric engineering at infinity, in a sense. So the idea is that if in the geometric engineering dictionary, you start from a string theory, you have your singularity, your conical singularity, you reduce the string theory on your singularity, and you obtain a field theory in d dimensions. The singularity, if it is conical, has a link, and if you reduce the string theory at infinity on this link, you end up with a field theory that has one dimension higher. This theory in one dimension higher is the symTFT. It's topological because the size of the link of the singularity is infinite, No? And so all dynamical degrees of freedom somehow decouple, and you extract some topological remnants of everything that survives at the link of the singularity. And one can recover the symmetry from branes and isometry, which is something that is kind of interesting and also a bit complementary to what was discussed by Sagar in her talk. One has to remind that in this context, what the effect arises from non-compact cycles that arise in the singularity, and one has a screening from the dynamical degrees of freedom that arise from branes wrapping compact cycles that give rise to these defect groups that essentially parameterize the various higher charges that are available in the theory. And then, like branes that are wrapping at infinity or locations of isometries at infinity end up acting on the defect, and one reproduces this type of picture. However, there is a caveat that I want to stress, because oftentimes this picture is drawn in a way that might be confusing. But I want to stress that, like the non-compact cycle here, this is a non-compact cycle is a field configuration that corresponds to a defect in d dimensions. So it is this point, no? And the linking and the non-compact brane in the SymTFT, this one all happens in the boundary. So it's important. I think that this is kind of important to remember, because otherwise one can get confused by this. So the SymTFT really is a d+1 dimensional field theory. No, and so it corresponds to geometric engineering on a Calabi-Yau, on the link of the Calabi-Yau. And then, of course, one has boundary conditions, and the boundary conditions arise from boundary conditions here. So we have boundary conditions also for the string theory, because it's on a non-compact space, and the fact that fluxes are non-commutative dictates the fact that these boundary conditions are non-commutative and give rise to the various choices that you obtain on this side. So this is the dictionary that can be established in this context. So like I'm saying this because, like, what I will say in the next part of the talk can be translated in these setups. And I think that it would be interesting, like it is an interesting exercise that has been done, and I wanted to remind you about it. Now, if you have this bulk boundary system, it is very interesting and useful to streamline the construction of topological interfaces. No? This can be done if you have in the bulk a zero-form symmetry of the SymTFT. If this zero-form symmetry of the SymTFT ends up having a non-trivial action on the topological boundary conditions, then using this sandwich picture, we can construct topological interfaces by shrink. No? This construction, like, in general, since this has a non-trivial action on this boundary condition, gives rise to a different gauge theory, to a different theory. But still, since the ending point is topological, this is a topological interface between these two different theories. This interface is non-invertible if, when you take this ending point of the zero-form symmetry in the SymTFT, and you fuse it with its opposite, you change the orientation of it and you fuse it with its opposite, you end up with something that is non-trivial. It is not just the identity. And I wanted to stress here that this computation is a computation that you do in the bulk, in the topological field theory. So it is the topological field theory that determines how this interface is non-invertible. So this is the first ingredient, and this is essentially graphically what I wanted to say. You know? So if you just compose this with its opposite, no, then you obtain an interface that goes from the theory back to itself, but the fusion of the interface with itself is non-trivial. Now, how do we use this? So this is about how do we use this to construct some non-invertible symmetry? No? So we have these conditions that we identified. So there is a non-trivial action, there is a zero-form symmetry in the SymTFT, there is a non-trivial action on the boundary, and the interface is non-invertible when in the bulk we compute the fusion of this ending point with its opposite, and we get something non-trivial. Okay. But there is a further condition that we need to establish a non-invertible symmetry, and this further condition is that this zero-form symmetry that we have in the bulk can be absorbed by the relative field theory. No? So if we take this codimension 1 defect in the bulk and we push it on the dynamical boundary, it gives rise to an isomorphism of the relative field theory. It can be absorbed by it. No? And if that is the case, then we end up with duality isomorphism between the various theories connected by these interfaces, by just composing this fact with the ending. And so, if that is the case, then we end up with a non-invertible duality symmetry where we have the duality which is obtained by this isomorphism, and the other one, which is another way, this topological interface, to go from the theory to the other one. These are the three ingredients that we need to build a non-invertible symmetry in zero form, non-invertible symmetry on the boundary. Okay, this is general. Like this logic applies in any dimension. To exhibit a zero form symmetry, ending points that happens in non-trivial fusion, and a boundary that can absorb it. Yes.
But I think that there is a topological method that implements the duality.
Mm-hmm. The duality is a statement, is a property, a feature of the boundary theory. It's the fact that the relative field theory can absorb this bulk zero form symmetry. No? This is a non-trivial requirement. Like it's not enough to just work with the topological side. No, you need also a property of the theory of the dynamical theory. This is what I wanted to stress here. The third requirement is a property of the dynamical theory that you have to establish it in a different way. You have to know about it to construct the non-invertible symmetry. Yes.
Let's say you have exactly a symmetry that has no zero form symmetries, but let's say high form symmetries, and we gauge these high form symmetries on a co-dimensional slide, so we construct a condensation.
Yes.
So this construction would work then.
Also, yes, I think so. Yes. You can also
construct like a zero form version of that. Like when we construct a condensation effect, we get zero form symmetry, so we can do this construction.
Absolutely, yes. And in fact, like most of the examples that will work in 4 dimensions are of that type. So this zero form symmetry is realized in the symTFT out of the condensation of some other topological operators. So that's exactly the right strategy. For those of you that don't know this technical word, condensation is an operation where one performs a gauging of a finite symmetry over a submanifold. So gauging a finite symmetry is essentially decorating your triangulation of your manifold with some symmetry defect and summing over all possible combinations that you can form. No? And so you can do this operation also on submanifolds. And this operation is the operation of condensation. It doesn't have to be confused with the operation of condensing an operator in our community, which is a different thing completely. The one is dynamical, the other is topological. But in condensed, this name comes from condensed matter theory, so this is why it's confusing. So now the thing is, in the construction that we have, in this construction, you can see that the defect that gives rise to the non-invertible symmetry is not a genuine defect of this TFT. It's like the boundary of something else. No? And so one can ask, like, is there a topological symmetry theory which realizes this defect on its own, no? In such a way that it is not the endpoint of something else. And that can be done by just gauging this zero form symmetry in the bulk. So if you can gauge the zero form symmetry, then this topological defect here in the gauged theory will just disappear, and you will be left with the ending points. And now they are genuine defects in the gauged theory. This was a remark by Kaidi, Omori, and Zheng that is extremely important for what we will do afterwards. So there is a new symTFT which is obtained from the one we started from by gauging this zero form symmetry. Okay, and that one is the symTFT that has the non-invertible duality defect as genuine defect, as genuine topological operators. They're not ending of other stuff. No? Now, in the 4D case, this construction applies when you have a 4D theory with one form symmetries. So let's review how that goes. It can be proven in this context that the symTFT is always equivalent to a topological BF theory that has the following gauge group. It's a gauge group which is a product of a billion factors. that has a prime decomposition. So you give me your theory, you can read off this gauge group. And the way we proved it in the paper is very simple. So we use the logic that I outlined at the beginning. No, we start from the anomaly inflow. In this case, the one-form symmetry. The anomaly is captured by a class in this group cohomology. You can look at it, compute it, and you can completely explicit because the one-form symmetry are always abelian. No? So this is a feature of higher p-form symmetries. They are abelian. The configuration space is a configuration space of things of higher codimension, and so they commute. There is not an order in which you bring them together, and so that's why these groups are abelian. You can compute it, and you end up with an anomaly that has this form. No? And in this form, there is a torsional term that trivializes on spin manifolds. And so we can neglect it in the context of the coarse classification that we have in mind. We can neglect this torsional part. We just end up with an action that looks like this. And these A are two-form finite gauge fields. And by a little field redefinition and the Chinese reminder theorem, you end up with a BF theory that has this gauge group, starting from this anomaly. Now, a fact is that in this BF gauge theory, now we have gauged this background two-form gauge field. We end up with surface defects, which are analogs of the Wilson lines. Okay, so whenever you have a gauge field, you can form a Wilson line out of it, and we have this surface defect. And this surface defect have a braiding, and this braiding is essentially captured by this coefficient. No? And here I'm using this notation because like it's a little bit more involved than that. So you have a pairing between classes in this H2, and the braiding, of course, depends also on the topology of the defect. And so this is how they are encoded in cohomology. You have a pairing in homology out of the position of the cycles in the bulk, and that has to be decorated by taking values in the defect group. And now, since you have this pairing, then you can classify the topological boundary conditions, and those correspond to Lagrangian subgroups of this defect group. These are maximally commuting collections of surface operators. No? This is what gives rise to the thing that we put on the left-hand side of the sandwich. So if we want to know you give me your one-form symmetry, you want to know what are the possible global structures that realizes that are associated to this one-form symmetry, just do this computation. Very straightforward. And you can realize the one-form symmetry just by considering the quotient. No? So you take the Lagrangian, and the one-form symmetry is whatever survives. Okay. Now, this is a bit of a summary of how it works for the various global forms, and this can be done very explicitly. And now that we have this, we want to find a zero-form symmetry for this bulk SymTFT. No? So how can we do it? So we have this braiding, we have this symplectic pairing on this defect group. It's essentially, if you think about it, it's just the Dirac pairing in 4 dimensions. No? It's something that says whether your charges are mutually local or not. No? And this choice of a topological boundary condition is essentially just a choice of what are the allowed line operators in your theory. It can be read between the lines of your gauge theory. Okay? It's just more compactly, it can be summarized in this. But since you have this braiding, this symplectic pairing, you can consider zero-form symmetry as something that is like a subgroup of the symplectic group with this pairing, valued in this defect group. And one can find relatively straightforwardly conditions, subgroups for which this condition 1, 2, and 3 that I have introduced before are met. No? So you just like look at your Lagrangians, find the ones that are compatible with this. But now I want to stress that when we gauge this bulk zero-form symmetry, when we go from the SymTFT associated to one-form symmetry to the one associated to the non-invertible symmetry defect, then we are introducing more topological defects. So in the gauged version of the SymTFT, there will be Wilson lines for these gauge fields. No? And these Wilson lines will also have a non-trivial braiding with the ending points that we created. Now they are genuine operators. You remember I had this description where we had this symmetry defect dg. They had ending points sigma. This ending surface is sigma, say, so something like that. No. And now in the gauged version, we lose this. We end up we remain with the sigma, which are now genuine, but we are introducing Wilson lines, and the Wilson lines for the gauged symmetry now can link these surfaces non-trivially, and this linking is giving rise to another Heisenberg type of Heisenberg algebra, and for this reason we have a larger Riedel space for this theory. There are more boundary conditions in the gauged version. Yes. Yes. Yes, you have to check that it is non-anomalous. You have to, if you gauge it, you have to check that it's non-anomalous. But in the cases we work with, these are always associated to condensations. And when you have condensation, typically the zero form symmetry you obtain is non-anomalous by construction. So you have this original twist defect and the Wilson lines, and you get these further boundary conditions. And these further boundary conditions are somewhat interesting, and I want to discuss a little bit. And moreover, you have a crossing action on the surface defect that you begin with. No? This crossing action is literally determined by how this subgroup of the symplectic group end up acting on the Lagrangians that are associated to those. So here I'm unpacking a little bit the notation. So you remember I said these topological defects are associated to classes in H2 with coefficients in the defect group. And in this formula, what I'm saying, I'm using an explicit description where I separate the support of the defect from its charge, and the action of the crossing happens on the charge. So if you cross one of these sigma with one, the sigma are codimension 2 in 5 dimensions, so you can cross them with a surface, and when you do, you end up with this crossing action on the charges of the symmetry defect. So these are useful because when you want to parameterize the boundary condition, you look for these Lagrangians, and in this context, you have to be consistent. They have to be Lagrangians also for the biased zero form, and they also have to be compatible with this crossing action. You end up with the labels parameterized by the Lagrangians for the surface operators, the Lagrangians for these Wilson lines and these codimension 2 defects in 3 dimensions, and there are some consistency conditions which are easily worked out exploiting this last equation. So this was perhaps very explicit, but also a bit abstract. So let's do an example. No? We consider the case of a quantum field theory in 4 dimensions that has a one-form symmetry Z2. Okay, so the CMTFT that we expect in this case is a Z2 BF theory. No? The defect group is 2 copies of Z2, because abelian groups have a dual which is the same, it's isomorphic. And the braiding is just determined by a symplectic pairing that is the symplectic pairing that says that the charges in the A subgroup are not mutually local with the charges in the B subgroup. Okay, so this is the braiding that we have. And if you look at this braiding for this defect group, the possible Lagrangian boundary conditions are just 3. One is the generator is associated to the generator of Z2A, the other is associated to the generator of Z2B, and the third one is associated to the diagonal. These are the Lagrangian boundary conditions. And now, if you consider in this context an example of an element of this SP Z2 times Z2 is S-duality, and S-duality has the role of swapping A and B. No? And so in our coarse picture, we work modulo P, and in this case, P is 2. So S-duality squares to -1. So usually you think about S-duality in 4 dimensions as a Z4 group. But from the perspective of the coarse classification, since -1 is 1 modulo 2, then it will just give rise to a Z2 zero form symmetry for the SymTFT. Okay. So this zero form symmetry of the SymTFT that we want to gauge is a Z2 symmetry. And when we gauge it, we end up with one Wilson line and with one of these non-invertible gadget, and this is the braiding that you get. You just pick a sign when they cross one another. When you swap them, this is the Heisenberg algebra. And so you have this boundary condition. Now there are 4 of them, and they are combinations. No, of the one is the one that sets the surface that annihilates, essentially absorbs the surfaces in the of A type, the one and the Wilson lines. The other one is the one that absorbs the surfaces of B type and the Wilson lines, the diagonal ones and the Wilson line, and then there is a 4th one which is associated to something on which the Wilson line cannot end, but this guy can end on it. No? So this is something that essentially corresponds to a boundary condition where you have a two-form symmetry now, which arises from gauging the sigma. And this one is a new boundary condition. Like it's like the philosophy is okay. It's gaugeable. We gauge it. When you gauge it, you end up with a new boundary condition. No? And from what we have observed, like we don't know whether this boundary condition is realized. Like of course you can construct examples. Like you can start from a classes theory, say, and show that you can gauge it. Then you end up with a new boundary condition. You can also do this in Maxwell theory, for instance. As duality in Maxwell theory, it gives rise to a non-invertible duality defect at a special value of the Maxwell coupling, and at that special value there is no anomaly for that for this Z2 subgroup, and you can gauge it. And what do you end up with? Probably self-dual Maxwell. It's as a no, what's it gonna be? But you can do this also for other theories, no? And what you end up with is a theory that has a degeneracy between mutually non-local degrees of freedom. So an answer, it's natural, like to think about it as some version of an Argyres-Douglas theory. No, it's something that has a degeneracy between magnetic and electrically charged degrees of freedom. But what I'm saying is that, from our coarse classification, there are a lot of these. You can read off what are the possible options. Now, so this is the setup. Okay, we know how to realize whatever symmetry, whatever non-invertible symmetry using this symmetry QFT. Okay, and now we want to use it to study gapped phases, but gapped phases that still have this non-invertible symmetry. Okay, so how do you do? Well, in this case, since we want a gapped phase, also the boundary has to be gapped. No? So before the boundary was any theory. Now, since we want a gapped phase, the boundary has to be gapped. And so we can use the classification of the boundary conditions, of the gapped boundary conditions, to study now like a symTFT where you realize a topological field theory in one dimension lower. No? Because it starts from a bulk which is topological, you put a topological boundary condition on one side, a topological boundary condition on the other, and then your isomorphism will give rise to a topological theory in one dimension lower. Okay? So in this case, it is the third condition that needs to be checked. No? So we need to find those boundary conditions that are such that this condition is met. So the topological boundary conditions such that they can absorb this zero-form symmetry. If I throw it at the boundary, it just leaves the boundary invariant. If I find them, then I obtain a gapped phase with a non-invertible symmetry. Okay, and it's just obtained out of this. So this is the task. If you want to understand what are the gapped phases in non-invertible symmetry, that's the task. We want to classify this. Let me save this. And so how do we do? Well, we know that the boundary condition correspond to Lagrangian subgroups. And so what we want to do is to find invariant Lagrangian subgroup of the defect. No, this is the strategy. And well, let me outline what we do in the simplest case. This is how one can do it. Consider, say, a group which is R copies of Zn, and a duality group which is generated by one element, which is a cyclic duality group, like this Z2 example. Using Chinese remainder theorem again, well, it's enough to consider n a prime power. And then, there are some technicalities in number theory that we have to use, because, turns out that this is very easy. It's more useful to essentially relate the Lagrangians over these finite fields to Lagrangians or invariant subspaces over the p-adic rationals. A bit complicated. But then, the point is that the linear algebra over these finite fields is just governed by the characteristic polynomial of the group element you start from. And if you have a G of a finite order, then this characteristic polynomial is just a product of cyclotomic polynomials. So it's just fact. And then, exploiting some tricks from Galois theory, you can show that when you want to study how this polynomial factorizes, this is just determined by p modulo n. This is just a bunch of theorems in number theory that you can use. Because the factorization corresponds to the possible invariant subspaces, and so you can do a classification. So, for instance, if you have m and k which are odd, and you consider a factorization of this type, then an invariant Lagrangian subgroup exists only if -1 is not a power of p modulo n. No, so it's a very very compact result. And this is easy to calculate. So the problem we started from was very hard, but once we have massaged it through some number theory, then we end up with something that we can code. And you code it. and you find some classification of this invariant Lagrangian. So whenever there is a blue check, then there are values of n and p, which is taken p modulo n, no? For which such invariant Lagrangian exist. So these are example where you realize a non-invertible gapped phase with one-form symmetry. It is possible. So this method leads to a first coarse classification of gapped phases, no? But then there is a question whether we can say more about this. So with this number theory magic, we can just, like, given the one-form symmetry, we can compute. Yes, please.
The other there was dots.
Yes, there are, like, we know more, but like for the sake of time, I wouldn't be able to explain. So there are further features of these boundary conditions that are associated to the other symbols. The table is just a copy of the table from the paper, and so like it's a bit hard to explain it, like, on the fly, but we can talk about it later if you're interested. Yes. But can we say more about this? Can we say more about these gapped phases? So the question is whether, like, we have these gapped phases, we know if they are consistent with the non-invertible symmetry or not, no? And one can ask whether these gapped phases are trivial or not. So do we have are there still some line operators in this vacuum? Is it a confined phase or not? And so, like, if there are no charged line operators, then the phase is trivial, and otherwise we can have a non-trivial topological order, some non-trivial theory that lives in the vacuum. And you can study this by just studying the interplay between these reference boundary condition you start from in the isomorphism and the infrared one that we have. And like, if you consider the intersection, then that's how you determine whether the phase is trivial or not. No? And there are also applications of these techniques to study the spontaneous symmetry breaking of non-invertible symmetry in 4 dimensions, if they are non-invertible. And they arise because, like, if we consider the SymTFT we started from, we see that this group will typically act on the various Lagrangians that we have, and they will typically not be invariant, and so they will form orbits. So we start from one and we generate others. No? But if we gauge this group, then in the gauged SymTFT, we can form a direct sum of these Lagrangians that are acted upon and mapped one into the other, and form a new invariant Lagrangian, but that one is not irreducible. No? So if you have a case like this, then that case is the one that corresponds to spontaneous symmetry breaking, because you end up with a system that flows to a collection of vacua, different ones, which are mapped one into the other by the action of the zero-form symmetry, and whose property are determined by this same trick. We just consider the intersection of the various Lagrangians that we end up, and we check whether the phase is trivial or not. So let's go back to our example. No? So we have our one-form symmetry Z2. The SymTFT is a Z2 theory. We have this A and B subgroup. They are swapped one another, and we have these boundary conditions. So let's consider one case. Let's consider a case where we have a sandwich. We fix a reference Lagrangian, which is our LA. And the symmetry preserving boundaries are the following. No? So this LA plus B and the LA plus B corresponds to the one that is the diagonal Z2 times Z2 subgroup. And so that one is left fixed by the duality. So that's an irreducible phase. And then, like, 0 or 2 denotes whether we can end on it the Wilson line or not, no? Or the sigma. But there is this other one, which is obtained by summing the two, the LA0 and LB0. It's a direct sum. The direct sum is invariant because they are swapped. So what happens if we consider the SymTFT picture? So here I draw a one-dimensional version where we have the Lagrangian on one side and Lagrangian on the other. Well, in this case, for instance, consider the first case. No, in this case, since there is this 0 label, this means that W can end on both. No, so if you think about the picture, like that we started from, no, if W can end on both, this means that here there is a point operator that is charged with respect to this non-invertible symmetry. And so this means that here we can have an order parameter for this spontaneous symmetry breaking, which is the ending point of W. No? Now, like, what is the structure of this vacuum is that there are two inequivalent vacua, which are mapped one into the other by the non-invertible duality symmetry. And you can see that the key feature in this context is that if you take the overlap of the first Lagrangian with the other one, you end up with a Z2 factor. And so there are still surfaces that we can stretch from one boundary to the other, which corresponds to the fact that there are some line operators here, which are the endpoints of these surfaces. And so we end up with a vacuum that has some non-trivial topological lines. It's a topological order, a Z2 topological order. While in the other case, you see that we compute the intersection between LA and LB. It's the trivial. You end up with just the origin of this Z2 times Z2 defect group, and this corresponds to the fact that this one is a trivial topological order. It's a trivial vacuum. So we reproduce the fact that if you have a spontaneous symmetry breaking of a non-invertible symmetry, the vacua that you obtain are different, can have different features. One is a topological order and the other is not. And this is exactly what was observed by Sergio, well, Argurio, and Francesco, and Christian, and collaborators. Ricardo, yes. So by their collaboration, as far as the vacuum of n equal to 1 star is concerned. So using this type of techniques, we can recover, for instance, the spontaneous breaking of a non-invertible symmetry just out of the SymTFT picture. In the other cases, well, one corresponds to a symmetry preserving where the zero form is realized and the one form is trivial in both vacua. And the last one is one where there is no zero form symmetry and the one form is trivial. So this is really like fully trivial. So like comparing also the other cases, so changing this LA into LB or LA plus B, or you can study and recover all the possible patterns of non-invertible symmetries in SU2 n equal to 1 star that have been observed from this SymTFT perspective. And also we observe the existence of global forms that are not realized that correspond to this extra Lagrangian. So also in this case there are more gapped phases, but those are not realized by SU2 n equal to 1 star. So an open question is there a theory that has that? Like, is there a gauge theory that has that one as a gapped phase? We don't know, but we know that compatible with this symmetry structure, there is this extra gapped phase. Well, is it realized? It's not. I don't know. Maybe. No. With the gaugeless duality, yes. In a sense, we know it exists, but the question is like, if you consider your study, for instance, you start from a gauge theory, it's n equal to 1 star deformation. You have a relevant operator. You perform the deformation. You can constrain the structure of the vacuum. You end up with these three choices. No? In this analysis, this analysis is just a coarse classification, and it's a classification based only on the symmetry structure. We don't have the dynamical mechanism by which you can flow to that specific phase or another. No? And so that's the challenge in a sense. No? So exhibit an example where there is an order parameter that triggers the RG flow that goes exactly in this phase. No? Maybe. Yes. Something that realizes this explicitly. Yes. It's also possible. I mean, I would take if you want to construct this with some class S theory, that would also fit. Like it might be that there is a class S theory that has a relevant deformation that maybe flows to something that realizes this, and this might be the right way to construct it. It's the topic of the next slide. It's possible. So this was for the case in which the zero form symmetry is abelian. But it is possible to do it also for duality defects that are not abelian. So those are very tricky to realize in Lagrangian field theories, but it is possible to build them using class S constructions. We know that we've seen reviews of class S in Alessandro's talk, for example. And in that context, we know that like it is the isometry groups of the ultraviolet curve that corresponds to the generalization of S duality. And so if you choose the ultraviolet curve in your class S theory in a nice way, you can find interesting realization of non-abelian duality groups that are like leaving that specific complex structure fixed. So this is an example from a Klein quartic that gives rise to an example of a non-abelian duality group. And the techniques that we have developed, while not systematic, can be used also to classify those. So we find, for instance, that there are gapped phases compatible with non-abelian duality defects. And an application of this, besides the one which is related to the question of Francesco, is about this symmetry-protected gaplessness. So the idea is that we have a classification of all possible gapped phases compatible with a given symmetry. No? So if you know that your theory has a symmetry which does not fall into this class, no? Then if you have a relevant deformation of that relevant deformation will flow to an infrared theory that is either gapless or such that your symmetry is spontaneously broken. No? And so, like, we have all this beautiful construction of classes theories where we can realize very interesting duality defects, very interesting structures, and exploiting the classes technology is relatively straightforward to build a deformation which is consistent with the symmetry, because every plumbing cylinder in the ultraviolet curve comes with an adjoint scalar. And giving mass to that adjoint scalar, you will just break the symmetry. And if you consider a combination which is left invariant by the action of the monodromy or of the isometry of the Riemann surface, you can build scalars that you can add as a superpotential deformation and lead to a deformation that breaks supersymmetry from class S to n equal to 1 or n equal to 0, no? Depending on their symmetry. Yes? It's explained in the paper, but the idea is that like if you have a like what is the idea? The idea is that you have your Riemann surface, you go to weak coupling limits, no, where you can use like you can like it has to be symmetric, so this goes on, no, and there is an action that acts on this Riemann surface by just rotating this, no. And then, like associated to these plumbing cylinders here, no, there will be some weakly coupled. You can take the generation which goes to weak coupling, and so these have like some description in terms of n equal to 2 vector multiplets. No, if the symmetry is such that it maps, it acts on the Riemann surfaces on the Riemann surface compatibly with this structure, then you can form an invariant, so compatible with the duality, just by taking the linear combination of all of these, for instance. No. And if you do a superpotential deformation, then it will preserve n equal to 1. But if you just give masses to the scalar, that will break also n equal to 1. No? And now, like the idea is does this flow to a CFT or not? No? And if you are in one of these cases which is not compatible with the gapped boundary condition, you know that like okay, it might, of course, like it might also break spontaneously. No, if it breaks spontaneously, then you end up with a gapped phase with a spontaneously broken non-invertible symmetry. But this maybe is a good starting point to explore the non-supersymmetric deformation of classes theories, because you know that if you start from one of these, then you just have to rule out the fact that the symmetry is spontaneously broken in the infrared. So you know that it cannot be gapped. No? So this would be this idea of symmetry-protected gapless. However, I stress this is very weak, no, because this is just essentially what I'm doing is like cinematic 2.0. No, it's not. No, I don't have a. I'm just playing with the symmetry. No, I'm not doing anything with the dynamics. So spontaneous symmetry breaking instead is a question about the dynamics. Is there a charged operator that picks a bet or not? No. And in the context of a deformation of the type that I'm suggesting for classes theories, hey, good luck. No, like there can like the moment you lose n equal to 2 supersymmetry, there can be anything. No, there can be dangerously relevant operator that comes in and break everything. So it's really like I think it's an interesting question, like for some of the people in the audience especially. So yes, but this can be used. This can be used as a guiding principle to study this question. No, so at least we know that there is a class of classes theories that is special that will not be gapped. No, and then you can go on from there. No. So yes.
If simplest explicit example was the
it can be do also for abelian ones. No. It doesn't need to be non-abelian. So, for instance, I think the V4 is one of the first examples where this type of effect can happen. No? Yes. Like you need to do. So you have to look at the. Say that we do the abelian case so that I can refer to the table. No. You tell me what is your abelian one form symmetry, and then you look at the table. No. And if what is the table? I skipped it. Here is the table, no? So if when you compute you start with ZP, you know what is the duality group, you can read it off from the action on the Riemann surface, no? That give rise to an explicit matrix that acts on the one-form symmetry lattice, no?
So classes have to have one form symmetry.
Yes, it has the one-form symmetry to begin with, and on top of that, it must also have this duality symmetry, no?
On the surface.
On the surface, yes. So you have to start with that, no? And then you know what is the order of the symmetry that typically is dictated by the, I don't know, do the case IN, that's dictated by N and the genus of the surface. And then the action of the isometry on the lattice of the Riemann surface gives you the explicit matrix for G. You compute the factorization property and you look at this table. If it's a cross, then you're in business. If it's a check, then it can be gapped. But if it's a cross, then it cannot be gapped. So it either spontaneous symmetry breaking or CFT. So that's the starting point, say, if you want to use this result towards this application. And then what can I say? Yes, possible generalization. No? So if you have a non-finite, non-invertible symmetry, the classification is much richer, and it's an open problem. But it's known that this is very fruitful. So we have results where matching the higher structure of these more fancy non-invertible symmetries, we can inform on the stability of the solitons of sigma models. So there is a nice application about adjoint QCD of this type. And also a classification of the corresponding gapped phases is not there. I don't know, like maybe using these techniques of symTFT for continuous symmetry, one can try to start classifying these gapped boundary conditions for both and check what happens. And yeah. Like Q mod Z, like these are I don't know, like is Q mod Z, I think it's finite. Some other, it's not finite, but it's not continuous either. No, yes. So that's what I meant by non-finite. No, yeah. Sorry. Yes. And then there are also possible further applications of symTFT for continuous symmetry. So from holography, we can construct them by taking suitable limits. I'd be happy to discuss them later. But if you think about spontaneous symmetry breaking for a continuous symmetry, the physics is completely different. No, like in one case we have gapped vacua, we have domain walls that separate them. The symmetry is fine. If it's spontaneously broken and it's continuous, then you expect to have Goldstone modes. So where are they in this language? Are they a feature of the symTFT? Are they like it's tempting to say so because it's the universality of the Coleman-West-Zumino effective Lagrangians. No? So there is this open question. This is something that we are currently investigating. And then all that I've said, essentially, can be extended in 5D and 6D. So there are some results about 60 cases that have been carried out by various groups. Also in 5D, we have some preliminary results. There are techniques from string theory to study these systems. But I know classifying boundary conditions, gapped boundary conditions, and these kind of things hasn't been done. And I don't know, like if you are after I don't know, a non-supersymmetric higher dimensional CFT, maybe you can get it from one that has a symmetry protected gapped non-invertible symmetry. Who knows? But it might be like an avenue to investigate this question. So it would be very interesting. I think this hasn't been done completely. Like it hasn't been studied. There are a lot of results in this context. And for 6D 1,0 theory, this becomes even more interesting because in 6D 1,0 you have 0 form symmetries and 1 form symmetries, and they mix. There is this 2 form defect group. Like it becomes very rich, the higher structure of symmetry of these models, which we have heard also in Sagar talks when she spoke about the 2 group structure of little string theories, for instance. So, and again, like if you know this data is extra checks on all dualities, you know, all like, so it's something that it's very interesting. So theories are dual, this higher structure have to match, and it has been used in various contexts, but the more topological defects we learn about, the more consistency checks we have for dualities. Conclusions. We have discussed some examples of applications of topological field theory techniques to inform the question about the dynamics of gauge theory in presence of non-invertible symmetries. And there is this remark. So if you have a gapped phase with non-invertible symmetries, it's extremely constraining. So constrained that you can really determine what is the gapped vacuum. No, this is like the $1 million question, but unfortunately, this is still like not realistic. But I think it's very nice as an application in field theory. And there are many open questions that remain. So our classification is very coarse. No. So we give up on spin structures. Well, there's the two classes that I mentioned that we can trivialize by suitably choosing the backgrounds. There is all possibilities that you can obtain by stacking SPTs that correspond to this second order obstruction in the papers by Francesco and collaborator, which we don't cover. So it's very interesting. It would be very interesting to refine these results. And then, well, the key question is how to inform the dynamics of the spontaneous symmetry breaking that out of field theory, no? And then yes, and these new boundary conditions that are they realized or not, and how. So thank you for your attention. This was it.
Questions?
Okay.
So you started from a SymTFT which has a BF theory and then gauged zero form symmetry to get a SymTFT which has extra boundary conditions. Is it relevant if there are anomalies of higher form symmetries or one form symmetries? Does that tell you something special? Also, can we gauge other like one form or higher form symmetries and generalize to that case? And would we get also extra boundary conditions, something similar?
Yes, I think that's relevant. Yes. So as I remarked with Francesco, so so there is an argument in topological field theory which states that essentially if you have a topological order, you can always build invertible interfaces in 5 dimensions between your topological order and the one we study. This result is very formal. Like we review it in the paper because we wanted to try to extract the physics of it, but it's literally very formal. It essentially amounts to the statement that you can always gauge like topological defect corresponding to line operators in 5 dimensions. Those can always be gauged. And by gauging them away, you can get rid of them and land on a theory with only surface operators. And you get rid of the point-like operators because you want to work with irreducible theories to begin with. So if you have a topological point, once you insert it in a correlator, that correlator will start splitting according to whether the topological point is inserted or not. And so you have a decomposition of your theory in universes, which you don't want. And so essentially, if you start from a theory that is realized with a symTFT sandwich, say, in 4 dimensions, then we believe that there will be invertible topological interfaces between whatever theory you start from and the one we have. So there is a way of mapping one into the other. However, from the physics perspective, these interfaces are dualities between different theories. No? So what we study is the case of only a theory that has one form symmetry, and out of the one form symmetry, it's anomaly, we read off this BF theory with surface terms. You have another theory that has more symmetry operators that corresponds to a 5-dimensional bulk gauge theory that is more general. Then there will be a topological interface that you can stack to that theory to map it to our symmetry sandwich. But that's a non-trivial exercise. So I think it's an interesting question. Does this address the question that you have? So that's like, if you want to do what you want to do, you need to construct this topological interface, and that's non-trivial. Yes.
Yeah, I wanted to ask about I think it's related to one question Francesco asked before. When you gauged the zero form symmetry in the bulk, so when you try to write down a explicit Lagrangian for in this case, the 5D field theory, I remember that back in time in the original paper of Kaide Moruchin, there was the problem that it was not gauge invariant.
Yes.
So I wanted to ask if there was progress in this.
We don't have an explicit Lagrangian, no.
Okay.
We know only that it has a collection of topological defects, and we know what is the algebra that they have to satisfy out of this construction, but we don't have a Lagrangian realization of that.
All right, let's thank Michele. And there's lunch.